Welcome to BYJU'S JEE, and this is the Target JEE Advanced video series. My name is Avinash, and in this video, I'll be covering the chapters Center of Mass, Collisions, and Conservation of Momentum. Now, these are sort of separate concepts, but very often in JEE Advanced, we find questions that involve topics from all these three concepts. So that's why we're combining them. Okay. So to give you a better idea of what is going to happen, first, I will go through the important concepts. I'll give you an idea of the weightages, right, in terms of the older papers, how frequent these concepts occur. And then we will solve some important problems. But then before we begin, please hit the subscribe button if you haven't already, and also the bell icon, because this will, of course, this way you can see more videos, and this will motivate us to make more of such videos. And if you think these videos are helpful, please make sure you share it with your friends as well. So let's begin. So let's come to the analysis in terms of number of questions. Now, we find that on average in JEE Main, there's generally about one question from these chapters and these topics. But last year in 2018, there were actually 3 questions from collisions in JEE Main. And again, in JEE Advanced, if you look at the last 5 years, on average, we get about 1 question per year amongst these topics. Now, the most frequent topics is collisions. Collision seems to be more frequent out of these 3. Okay. So let's look at this problem. It says that a thin disk of radius R and mass M is kept on a table, is rotating about its center with an angular velocity of omega. Find the force applied by one half of the disk on the other. Okay. Now, at first look, this might feel a little complicated. How? So we have a disk that's rotating with an angular speed of omega. It has mass M and radius R. How do you find the force that one half applies on the other? Because there are multiple points of contact. If I just had to split it like this, then you'll notice that this one half is touching the other half with multiple points. It's almost impossible to figure out how much force will be applied at each point. So how will you go about this problem? So let's just quickly go through the thought process. So we know that we have to analyze what's happening with one half. So let me separate it. Let me just draw one half separately. So let's say this is that half. I'm going to draw it separately. Now, what are the forces acting on it? Of course, there's gravity and normal force, but we don't have to worry. That's in the vertical plane, and we're not worried about that, right? Because this is on a table, which means it's horizontal. We only have to be worried about the forces that's coming from the other half. And we know that it's probably something like this. I mean, we don't know the direction, we don't know the magnitude. It can also be somewhere in this direction. It might have components in this direction, so on and so forth. So we know that these are the different forces. But how will we calculate the magnitude of this force? So we know that F, let's say F net, is equal to M into A, right? But this is for a point mass. When we have a rigid body, what happens? We know that this is equal to, let's say, capital M, which is the mass of the whole body, into A, which is acceleration of the center of mass. So F net equals M into A into center of mass. Okay, A of center of mass. So now we're getting somewhere. Now we have some idea. Now what will this M be? M is already given to us. So M, let's not confuse, let's say this is small m only. But small m will be equal to capital M by 2, correct? Because it's half the disk. Okay, that's fine. So that we know. But what about the acceleration of center mass? How will you calculate the acceleration of the center mass? So let's first find the position of the center mass. The position of a uniform semicircular disk, we know, is somewhere over here, right? At a distance of 4 by 3 pi into r. So this distance from here to here will be 4 by 3 pi into r. R being the radius of this disk. So this is the position of the center mass. Okay, how do you calculate the acceleration of Well, we know that this disk is rotating, which means that the center of mass of this disk should also rotate like this, right? It should go around in a circle about the center of this disk, like this. What will be the acceleration of the center of mass? Now we know already that because the disk is rotating with omega, that the center of mass should also go around with the same angular speed omega. Okay. Then, if this distance is 4 by 3 r, then the acceleration, in this case a should be equal to omega square r dash, right? Acceleration of the center of mass, I'm saying, should be equal to omega square r dash, where r dash is the distance between the center of mass and the center of the disk. Or in other words, this should be omega squared into 4 by 3 pi into r. Then, if we know that this is the acceleration, then this into the mass of this body should give us the net force, right? So, which means if I substitute this over here, I'll find that this will be equal to m by 2, which is the mass, into omega square into 4 by 3 pi into r. So yes, this is your answer. Now you can of course simplify this. 2, so we have 2 by 3 pi into m omega squared r. Now this is the final answer. This is the net force. Now this might seem like a weird way to do this problem, but if you notice, we're using the concept of center of mass very cleverly over here. So I'll just quickly go through the reasoning. So we know that this object is rotating, which means its center of mass should be going through circular motion. That's correct, right? And we know the position of the center of mass because it's a uniform semicircular disk, which will be at a distance of 4 by 3 pi into r from the center. Okay, it's fine. And we also know that since that point, the center of mass is moving in a circle, its acceleration will be equal to omega square r dash, right? That has to be true because it's moving in a circle. So that will be equal to omega square into 4 by 3 pi into r. And so finally, that if you multiply into the mass, we get, because that is the acceleration of center of mass, and that into the mass should give us the net force. That's what we started with. So this is how we find the answer. Cool. Let's see what we have in this problem. So right now we have a block moving along a horizontal surface like this with a speed of 4 meters per second, and this is an instantaneous speed. Okay, the coefficient of friction is given. It's given to be 0.2. And we have another ball. Yes, it's falling down or hitting this ball with a box speed of 5 meters per second. Then it bounces back with the speed of 3 meters per second. Find the final speed of the block after collision. So we have to find out the speed of the block after this collision occurs. But what's happening here? You might immediately, at this point, you might think, how can the block be affected? Because the ball is applying a vertical force, right? Why will that affect the block in any way? Because the block is moving in the horizontal direction, correct? Well, it will affect the block because that will momentarily increase the friction, right? Also, you need to understand that, see, this is not moving at a constant speed because there is friction, which means that the block is decelerating. It's already moving. Right now, it's at the speed of 4 meters per second, but it's already decelerating. And at this point, when the ball hits, the normal force will increase, right? The force from the surface will increase, and because of that, the frictional force will momentarily increase, and it'll increase by a large amount, and therefore that will cause an impulse, and because of that, there will be a change in momentum, and therefore there will be a change in speed. So we need to find basically the impulse provided, or the impulse created by friction. Okay, and that will give us the change in momentum, because the only force in the horizontal direction here is the friction force. There is no other force in the horizontal direction. So how do we do this? Well, we know that the net, let's say, horizontal impulse is equal to integral f dt, right? But that force, that F, is basically the frictional force, right? That's the only force that's creating impulse over here. So that will be equal to, and we know the friction has to be equal to mu into n. F is equal to mu into n. So this will be integral mu n into dt, right? Okay, since mu is a constant, comes out, that becomes integral n dt. So now we found that the impulse produced by the friction force is equal to mu into the impulse provided, or the impulse produced by n dt, into the impulse produced by the normal force, because integral n dt is the impulse produced by the normal force, right? So how will we find out the impulse produced by the normal force? For that, let me draw the free body diagram of that block during collision. So it's like this. The ball is here, it's colliding with the block. So let's draw all the forces acting on it. So there'll be a normal force from the ground, let's say somewhere over here. Let's call this N. There will also be an impulsive force or a collision force from the ball, right? And of course there will be mg in this direction, in the downward direction. Like these are the only three forces acting on the block in the vertical direction, correct? So we can say that N, right over here, N should be equal to F plus mg, right, at that point. Which means that the impulse produced by N, which is equal to integral n dt, should be equal to integral f dt plus integral mg into dt. Now, in these kind of cases, what we do is we actually neglect this term, because the magnitude of the force mg is actually very small, right? Now, if you take mg into dt, dt is so small that if the magnitude of the force is too small, it becomes negligible. Whereas in the case of the collision where the ball is hitting, it is a substantial amount, because the magnitude of the force F will be very, very large. It won't be constant, but the overall magnitude will be very large, right? So therefore, it's not an insignificant number. So we can neglect this term. This integral mg dt can be neglected, and we can finally say that integral n dt will be equal to integral f dt, where f is the impulse provided or the impulse created by the collision force, or the force from the ball. Okay, so let me just write that over here. This becomes nu into integral f dt. What is integral f dt? As I said, that's the impulse produced by that collision force, but that's also equal to the change in momentum of that ball, right, of the ball itself. So I can say that this finally becomes mu into delta p, where p or delta p is the change in momentum of the ball itself. Okay, now we can solve this problem. So finally, let's find out what this mu into delta p is. We know that the mass of the ball is it's given to be 2 kgs, right? So initially, let's say downward direction, just for simplicity, let's assume downward is positive, then integral f dt should be equal to this f over here is friction. Let's not get confused. And f dt should be equal to mu in just 0.2, right, into change in momentum. Change in momentum will be mass into change in velocity. Mass is 2 kg, so into 2 into change in velocity. Let's say if downward is positive, then final velocity will be equal to, it's coming up with -3, right, minus initial velocity, which is 5 in the downward direction. So this will be equal to 0.2 into 2 into minus 8, which is equal to 0.2 into minus 16. Right? And minus 16 into 2 will be what? 32, 3.2 minus 3.2. That's the units will be Newton seconds. So finally we get that the impulse produced by friction is minus 3.2 Newton second or 3.2 kg meters per second. The units don't matter, right? So what we need to understand is that the magnitude of the impulse is 3.2. This means that because friction is acting in the opposite direction to the initial speed of the block, then this means that the momentum of the block should reduce by 3.2 kg meters per second. That's what it means. So the net impulse acting from friction is 3.2. So the net momentum should reduce by this amount. So this gives us that the net impulse produced by friction is 3.2. It says here it's minus 3.2 Newton second, but we don't have to worry about the negative over here. The magnitude is what we really need to worry about. So this tells us that on that block, the net impulse that's coming because of friction is 3.2 Newton second or kg meters per second, and this means that its momentum is going to reduce by that amount, because net impulse equals change in momentum, because this is the net impulse, because friction is the net force acting on it in the horizontal direction. So the net change in momentum will be 3.2 Newton kg meters per second, and we obviously know that the momentum has to reduce because friction is opposing motion, right? The speed has to reduce, which means that the final speed will be lesser, right? So I can say that 4 into the initial speed, which is 4, minus 4, which is the mass again, into the final speed. Here 4 is the mass, and 4 is the initial speed, and 4 is the mass again, and v is the final speed. This should be equal to 3.2, because this is the net impulse, and that should be equal to change in momentum. Okay, I'm just saying that the change in momentum should be equal to 3.2. This implies that 16 minus 4v should be equal to 3.2, right? Now if I simplify this, I get 4v equals 16 minus 3.2. How much is 16 minus 3.2? That will be 12.8. 12.8. So we get v is equal to 12.8 by 4. Yeah, finally we get 3.2 again. Surprisingly, we get 3.2 meters per second. So the final speed will be 3.2 meters per second. So it will reduce from 4 to 3.2 meters per second. So just to give you a quick recap, if this was a little confusing. So initially we saw that the block is reducing in speed, and that's happening because of a change in impulse, or change in momentum or an impulse from frictional force. To calculate the frictional force from here, we use this. The frictional force, the F or impulse because of frictional force, should be equal to integral mu n dt, which is equal to mu into integral n dt. Now integral n dt is nothing but the impulse produced by the normal force. So to find that out, we went to the free body diagram and we found that the impulse produced by the normal force should be equal to the impulse produced by the collision force, right? And that should be equal to the change in momentum of this ball. So we finally found that the impulse produced by the frictional force should be equal to mu into delta p, where delta p is the change in momentum of that ball. And then from there, we calculated this impulse produced by friction. Then we found that this should be the change in momentum of this block. That's how we calculate the final speed. So let's jump to the next problem. In this problem, we have two blocks connected by a spring. One is a spring, then block number 2. Now, what's in the initial condition, what we have is that the first block is going to start moving at 9 meters per second, and this one, it has a mass of 4 kgs. Second block, whose mass is 3 kg, of course, is initially stationary. The question is, find the maximum compression in the spring when this happens. So, moving starts at 9. Now, how do you find this out? Well, what do we know here? See, obviously we're going to assume that this is frictionless, the surface is frictionless. Now, when this 4 kg block is coming like this, right, it's being pushed, let's say, it's starting with a speed of 9 meters per second. Now, that is going to compress the spring, and that means that the spring now is in a compressed position, so it's going to apply a force in both directions, right? Which means it'll push the 3 kg block as well. So the whole system will start moving, correct, in the direction. Now, how will you find out when there's maximum compression? It's very weird, right? It's hard to figure out what now. If the 3 kg block were stationary, then it makes sense that maximum compression it's very easy to find out. But because the 3 kg block is also moving, then now what happens? How will you find this point? Well, a nice way to do this is I know the whole system will start moving in this direction, but if you start looking at, let's take this frame. If you look at a frame that's moving along with the 3 kg block, okay? Now let's say you're sticking to that frame, so you're moving along with the 3 kg block. And with respect to that frame, maximum compression will happen when the 4 kg block comes to rest, right? Because let's say this is a 3 kg block. With respect to the 3 kg block, the 4 kg block is going to come like this, stop, and then move back. Of course, from the ground frame, it'll happen like this, both of them move. But in that frame, right, in the block which is at rest in the frame which is at rest with respect to the 3 kg block, which is this over here. Now, with respect to that, the 4 kg block will come like this and then start moving like this. So, you can say that when the 3 kg block, when both these blocks are at rest with respect to each other, only then the maximum compression will happen. So, in the ground frame, when both these blocks are moving with the same speed or the same velocity, that's when the maximum compression will happen. Okay? Cool. So now that we know this, then the problem becomes somewhat simple. So what will we do? We'll assume that now let's not solve this in the frame that is at rest with respect to the 3 kg block. Let's solve it in the ground frame because it becomes easier then. How do we find that speed where both of them are at rest with respect to? So basically they're at the same speed. We can conserve momentum because initially only the 4 kg block is moving, right? So the initial momentum, it's called Pi, will be equal to 4 into 9, right? Which will be equal to 36 kg meter per second. The final momentum will be when both the blocks are moving, but they should be at rest with respect to each other. So let's call it Pf will be equal to 3 into V, V being the final speed where both of them are moving, plus 4 into V, right? Or this will become V into 3 plus 4, 7V, right? So this, if you conserve momentum because there is no net external force acting on this, you can say that 7V should be equal to 36, or V should be equal to 36 by 7, which will approximately equal to 5.14. Right? So when maximum compression is happening, the speeds that they'll have will be 5.14 meters per second each. Right? Now, what do? We need to calculate, what does the question say? We need to find maximum compression. How do we find maximum compression? You can use one more idea or one more concept, which is conservation of energy. Some other color. Right? So let's conserve initial energy and final energy. Initially, what is the total energy of the system? It's just the kinetic energy of the block, right? So that initial energy EI will be equal to half m, which is mass of the block, is 4 into 9 squared. Right? Okay. Then the final energy of the system will be what? Will be the kinetic energy of the blocks, which is half 4 into, how much is that? 5.14 squared. Plus again half into 3 into 5.14 squared. 3 being the second block. Plus, what else? Now, the spring will be in its compressed state, right? Maximum compressed state. So therefore, it will have potential energy, and that will be equal to half kx squared. Correct? Where x, let's assume, is the maximum compression. Cool. So then we just have to solve this. So we have equation 1, which is the initial energy, and we have equation 2, which is the final energy. K is also given to us, which is 8. K is equal to 8 Newton per meter. This is given to us. So now we just have to equate this and find the value of x. Right? It's a simple algebra. If you do that, we'll find that x is equal to 4.16 meters. This is your final answer. In this problem, we have a rod that's something like a rod. What's this? A body. Okay, we have a body, a horizontal body like this, but it's stuck. It's kind of tied to the ceiling in a weird manner. This is our body, and it's tied or is hanging from 2 ropes, not 1 rope. Okay, length is L. And mass capital M. What we have to find is the velocity of the bullet. Oh, sorry, I forgot to mention that there's another bullet here of mass small m that's coming in. That's what we need to find. It strikes it, so let's say we call this V dash. Let's call this V. It's coming in with the speed V. Okay. And it hits this body, this horizontal body, and then gets stuck to the body, and the body moves up like this, obviously, right? The question is find this initial V. Simple. So the question tells us that the threads move up through an angle theta. Cool. So how will this move? Now, some of you might get a little confused here. So that how the body moves is probably the most important part of this question. You might think that it'll move like that. Let's say this is your body and it's a hit. You might think that it'll move like this, but the truth is it won't, because every single point on that will have to undergo circular motion, or rather, this point and this point, both these points will be moving in a circle, right? Because they have a constant radius, right? So which means that if this is the object, it'll move like this. Okay, it'll always remain horizontal. So if I had to draw the final position, it'll be something like this. Yeah, something like this. So the rod will move up like this. Cool. So let's assume that this angle is then theta. Right? It's going up with this angle theta after this bullet sticks to this body. Now what do we do? So one thing we can do is we can use conservation of energy and find the velocity of the combined system, that is the bullet plus this body together. Once it sticks, right, that it'll have an initial velocity. That velocity we can find using conservation of energy. Okay, so let's call that, I'm going to call it V dash. Right, that's basically the velocity of the system after collision. Okay, so if you do that, then the initial kinetic energy or the initial energy of the system will just be, say, E1 will be equal to half m plus small m into V dash squared, right? This is the initial energy of the system. What's the final energy of the system? E2. So it's going to go up and then it's going to stop. So it'll have final kinetic energy will be 0. Fine. Will there be work done by gravity? Yes, right? Or you can say that there's a change in potential energy and the potential energy will increase. So the final potential of the system will be equal to, if we assume that this delta is h, let's say that this, if this distance is h, right, then it should be m plus m into g into h. What is this h equal to? Well, we know that this length of the string is L, and this distance from here to here, from here to here, that distance has to be L cos theta using simple trigonometry. So h should be equal to L minus L cos theta, right? So h should be equal to L minus L cos theta, right? So E2, which is the potential energy of the system, will then be equal to, different color, m plus m, which is the mass of the system, into g into L minus L cos theta. Right? This will be the final energy. Is there anything else? Now, some of you might have a question here. Like, what about the work done by the string itself? Because in the other normal pendulum cases, force by the string will always be perpendicular to the displacement at any single point. So therefore, there will be no work, correct? That's why we neglect the work done. But over here, this is not similar, right? This is a different case. But if you notice, at every single point, the point of where the string is attached to the body, that point is always moving tangential, right? Or rather, say that it's moving in a circle, which means that the displacement of that point will always be, again, perpendicular to the tension force. So therefore, we can assume that the work done by the tension is 0 in this case as well, right? So there's only work done by gravity. There's no other work done. Okay. So then these two will basically be the energies. Now we just have to equate the energies because energy has to be a constant. Write down over here. So I get half E dash squared should be equal to m plus L cos theta. Okay. Now, if I solve this, I can just cut off m plus m, right? Because assuming they can't be 0, so therefore we can cut them off. Then E dash squared equals theta. Implies that E dash equals this is your value for V dash, right? And please keep in mind that this is the velocity of the system after collision. Now what do? No, but we have to find the velocity of the bullet before collision. So for that, we conserve momentum. Okay. So in the previous, just before the collision, the initial momentum was, let's call it Pi, was equal to m into V, right? And this is the V that we need to find. And the momentum just after collision will be what? The mass of the system, which is small m plus capital M, this, into the velocity, the speed of the system, right? Just after collision, which you just found out, and that is V dash. We can still conserve momentum, even though there is, you might think that there is a net external force from the string, but at the point of the collision, the string force is which is the tension, which will be impulsive, but that will be perpendicular, right? Completely perpendicular to the line of impact. So it will not affect the momentum in the horizontal direction. So we can still conserve the momentum in the horizontal direction, right? So therefore, we have MV should be equal to M plus capital M into V dash. We just found. Right, now this means that V should be equal to M. Bring this side. Yep, so that is your final answer. Let me just check. Yeah, so that is your answer.
For more videos and live lectures on the JEE, click on the subscribe button now.